Welcome to our explainer on the American Concrete Institute's Report 351.3R18. Today, we're uncovering the invisible, super-strong engineering that keeps massive industrial machines securely grounded. Let's jump right into this structural blueprint and map out exactly how engineers prevent heavy machinery from literally shaking buildings to the ground.
Here's our agenda. We've got 1. The Dynamic Machinery Challenge. 2. Types of moving machines. 3. Designing the perfect foundation. 4. When foundations fail. And 5. Repairing and upgrading foundations.
Section 1. The Dynamic Machinery Challenge. The problem with power.
So, what keeps massive industrial machines from shaking themselves apart? It's a fascinating question, right? I mean, if you've ever stood next to a roaring gas turbine or a massive diesel engine, you know they generate some violently dynamic forces. We aren't just talking about the dead weight of a machine resting on the floor. We're talking about extreme kinetic energy. If you've ever felt the ground vibrate blocks away from a power plant, well, you've felt just a tiny fraction of the forces these machines generate internally.
The American Concrete Institute lays out a massive challenge here. Quote, "Precise machine alignment should be maintained and foundation vibrations should be controlled to ensure proper functioning of the machinery during its design service life." End quote. You see, the goal isn't just to hold the machine up. No way. The goal is to maintain absolute pinpoint alignment and aggressively control vibrations for the entire lifespan of the equipment. Without these carefully engineered foundations, that immense power would literally tear the machine and the facility to pieces.
Section 2. Types of moving machines, the source of the shakes. To build the perfect foundation, we first need to understand the machines themselves. The physics at play are pretty incredible. In rotating machinery, even a microscopic offset, just a tiny unbalance in a rapidly spinning shaft, creates a massive, constant outward inertia force. Think of a washing machine that's heavily loaded on one side during the spin cycle, but scaled up to thousands of horsepower. That unbalanced mass fundamentally wants to rip the entire machine right off its center of rotation.
Because of these wildly different forces, foundations have to be designed completely differently based on the machine type. On one side, we have rotating machinery, like gas turbines and large motors. They have a continuous, smooth spin that creates those constant outward forces we just talked about. But on the other side, we have reciprocating machinery, like diesel engines or massive compressors. These use a pulsing slider crank mechanism. They don't just spin, they punch. They create violent, repetitive impact frequencies that hit the foundation like an absolute jackhammer.
Section 3. Designing the perfect foundation. The hidden hero.
This brings us to a highly complex puzzle for engineers. You can't just pour a giant block of cement and call it a day. The engineering required here is deeply sophisticated. They have to calculate specific site conditions, like soil impedance, which is essentially how much the ground naturally resists movement, and dynamic shear modulus, meaning how the soil responds to rapid twisting forces. They also have to account for the exact configuration of the machine base, the anticipated turbulent loads during startup phases, and strict environmental factors. Basically, every single foundation is a custom-engineered response to its specific environment and machine.
Think about it like this. A dynamic foundation is not just sitting there passively. It's an incredibly active shock absorber. It acts like an anchor in a stormy sea, actively resisting, dampening, and safely transmitting those violent outward pulls and repetitive punches downward into the earth, without vibrating the surrounding building into dust.
Section 4. When foundations fail, the breakdown. Of course, things don't always go perfectly. Sometimes forces are just too great, a design was flawed, or equipment operating speeds change over time. The warning signs are usually pretty clear, but highly destructive. If a foundation is made too tall and narrow, or if a mechanical repair alters the machine's rotating weight by even a small amount, the whole system falls out of balance. You'll start to see severe foundation rocking around the horizontal axis. You'll hear and feel high vibration from the equipment, and soon you'll get dangerous cracking in the concrete and grout, eventually leading to total anchorage failure.
This creates what engineers essentially view as a terrifying cycle of degradation. Step 1. Unchecked vibrations. Step 2. Those vibrations start to deteriorate and crack the concrete. Step 3. That cracked concrete no longer holds the anchor bolts securely, so they loosen up. And Step 4. What happens when the bolts loosen? The machine vibrates even more violently. It's a compounding, rapid feedback loop that will completely destroy the setup if left alone. Early intervention is absolutely mandatory.
Section 5. Repairing and upgrading foundations, stopping the cycle.
Fortunately, when this cycle begins, it's not necessarily the end of the line. Engineers have a brilliant toolkit of advanced repair techniques to save the machine and the structure. If a foundation is rocking or cracking, they can literally drill and install vertical post-tension bolts right through the cracked sections, pulling the whole block tightly back together. They might add foundation mass, widening the concrete base to give it a broader stance and stop the rocking. They can upgrade anchor bolts to higher-strength alloy steel, replace the failing upper concrete with a dense reinforcing bar grid, or use poured polymer chocks for a flawless, custom-fit connection to the earth.
Now, when engineers have to replace that degraded top layer, they don't just pour standard concrete back in. They often use a supercharged material called polymer-modified concrete, or PMC. This is a specialized concrete with superior tensile and flexural strength, better adhesion, and less heat of hydration than standard ready-mixed concrete. Because the repair is already happening in a compromised environment, PMC is an absolute game changer. It bonds beautifully to the old foundation and aggressively fights off future cracking.
Another incredibly effective upgrade happens right at the connection points. By simply upgrading to high-strength ASTM A193 Grade B7 steel anchor bolts, the machine is clamped down with incredible force. This massive increase in clamping force transfers the vibratory forces much more efficiently down into the earth, stopping those destructive vibrations in their tracks and completely breaking the cycle of degradation.
It really gives you a whole new appreciation for the concrete beneath our feet, doesn't it? Next time you feel a rumble from a power plant or a factory, consider what invisible, dynamic engineering is fighting to keep the world stable beneath your feet. Thank you for joining me on this explainer, and I hope you never look at a block of industrial concrete the same way again.